gravity is a force. That is what most of us were taught in school. Mass pulls on mass, the earth pulls on you, the moon pulls on the oceans, the sun pulls on the planets. It sounds simple, intuitive, almost obvious. Drop a ball and it falls. Of course, it falls. Gravity is pulling it down. For more than 300 years, this idea worked so well that it became one of the most trusted descriptions of nature ever written. Isaac Newton even gave us the equation. Multiply two masses together, divide by the square of the distance between them, multiply by a constant, and you can predict the motion of planets centuries into the future. Using that equation, scientists predicted the tides of the oceans, the paths of comets, even the position of planets that no one had seen yet. It was so accurate that in the 1800s, astronomers used Newton's formula to discover an entirely new planet, Neptune, simply by calculating where an invisible gravitational pull must be coming from. When a theory lets you discover a planet using nothing but mathematics, you tend to trust it completely. And yet there was always something deeply strange hiding inside the idea of gravity as a force. Something Newton himself worried about. Imagine a ball falling toward the Earth. The Earth and the ball are not touching. There is no rope between them, no rod, no physical connection. Between them is empty space, vacuum, nothing. And yet, somehow the Earth knows the ball is there and pulls on it instantly. How does it know? How does a piece of matter reach across empty space and grab another piece of matter without anything in between carrying the message? Newton called this action at a distance, and even he admitted it felt absurd. In fact, he wrote that the idea that one object could act upon another through empty space without any physical mechanism was so strange that no thoughtful person should easily accept it. But the equation worked, so for more than 2 centuries, physicists used the formula and ignored the mystery. Gravity pulled, objects fell, planets orbited. The universe seemed simple until small cracks begin to appear in the story. And once you see those cracks, you realize something extraordinary. The force you think is pulling everything together might not exist at all. For more than 2 centuries, Newton's picture of gravity worked almost perfectly. The equation was simple, elegant, and astonishingly accurate. If you knew the masses of 2 objects and the distance between them, you could calculate exactly how strongly they would pull on each other. That single relationship explained why apples fall, why the moon orbits the Earth, and why the planets trace graceful paths around the Sunday. Engineers used it to design bridges and harbors. Astronomers used it to predict eclipses decades in advance. Space agencies used it to send spacecraft across billions of kilometers of empty space and guide them precisely past distant planets. When the Voyager probes were launched, their entire trajectory relied on Newton's gravity. By swinging close to Jupiter and Saturn, they stole a tiny piece of each planet's orbital motion and used it, like a slingshot, to accelerate toward the edge of the solar system. Every maneuver was calculated with Newton's equation, and every one of them worked. This was not a fragile idea. It was one of the most battle-tested theories in the history of science. And perhaps the most dramatic demonstration of its power came in the 19th century. Astronomers studying the planet Uranus noticed that its orbit was slightly wrong. It drifted just a little from the path Newton's theory predicted. Instead of assuming the law of gravity was flawed, 2 mathematicians working independently reached a different conclusion. If the orbit was disturbed, something unseen must be pulling on it. Using only Newton's equation, they calculated where this invisible object should be located in the sky. In 1846, the German astronomer Johann Gaia pointed his telescope exactly at the predicted location. Within an hour, he found a new planet, Neptune. A world no human had ever seen had been discovered with nothing but mathematics and the idea that mass pulls on mass. When a theory allows you to predict the existence of a planet before anyone has observed it, the natural reaction is simple. You trust the theory completely, and for a very long time, physicists did exactly that. But hidden beneath this extraordinary success was a small and stubborn problem that refused to go away. A tiny mismatch between theory and reality that would eventually force scientists to rethink gravity itself. But eventually a crack did appear. It was small, almost embarrassingly small. In fact, it was so tiny that for many years, scientists wondered if it even mattered. The problem involved the planet Mercury, the innermost planet in our solar system, the one that circles closest to the sun unday. Like the other planets, Mercury travels around the sun in an elliptical orbit, but that ellipse does not stay fixed in space. Very slowly over time, the orbit rotates. Astronomers call this motion the precession of the perihelion. If you imagine the orbit as an oval drawn around the sun, the long axis of that oval slowly turns like the hand of an extremely slow clock. Now, this rotation was not unexpected. The gravitational pull of the other planets slightly disturbs Mercury's path, and Newton's equations can calculate those disturbances with remarkable precision. When astronomers added up the effects of Venus, Earth, Jupiter, and the rest of the solar system, almost the entire motion of Mercury's orbit could be explained. Almost, but not quite. After accounting for every known gravitational influence, there remained a tiny leftover shift, about 43 arcsecs per century. To give you a sense of how small that is, 1 arcsec is 13/600th of a degree. 43 arcsecs over an entire century is an almost unimaginably tiny angle, and yet it refused to disappear. Decade after decade, better measurements confirmed the same discrepancy. The orbit of Mercury was drifting slightly more than Newton's theory predicted. At first, scientists assumed the explanation must be similar to the discovery of Neptune. If Uranus had been pulled by an unseen planet, perhaps Mercury was also being disturbed by something hidden. The proposed planet was even given a name, Vulcan. It was supposed to orbit closer to the sun than Mercury, invisible most of the time because of the sun's blinding light. Astronomers searched for it for decades. They watched during solar eclipses, hoping the temporary darkness would reveal the mysterious world. Expeditions were organized across the globe. Several astronomers even claimed to see it. But every supposed sighting eventually turned out to be a mistake. Vulcan was never found because it did not exist. That left physicists with an uncomfortable possibility. The problem was not a missing planet. The problem might be the theory itself. Newton's law of gravity, the equation that had predicted Neptune and guided centuries of science, could not quite explain the motion of Mercury. The discrepancy was tiny, but it was real. And sometimes in physics, the smallest anomalies are the ones that matter most. They are the cracks that reveal a deeper truth hiding underneath an otherwise perfect theory. The problem with Mercury was troubling, but it was not yet a crisis. Scientists had seen discrepancies before, and usually the explanation turned out to be something simple: a new planet, a measurement error, or a small correction to the calculations. But while astronomers were still searching the sky for the imaginary planet Vulcan, another idea was quietly emerging that would make the problem far more serious. At the beginning of the 20th century, a young physicist named Albert Einstein was thinking about something that seemed completely unrelated to gravity. He was thinking about light. In 1905, Einstein published the theory of special relativity, and one of its most important conclusions was radical. The speed of light is not just fast. It is the ultimate speed limit of the universe. Nothing can travel faster than light. Not matter, not energy, not information, not any influence of any kind. This limit is built into the structure of reality itself. Now consider what this means for Newton's gravity. In Newton's picture, gravitational forces act instantly across any distance. If the sun were to suddenly disappear, the Earth would immediately feel the loss of its gravitational pull and fly off into space in a straight line. The change would happen everywhere in the universe at the exact same moment. But according to Einstein, this cannot happen. Information about any change cannot travel faster than light. The sun is about 150 million kilometers away from Earth, and light from the sun takes about 8 minutes to reach us. If the sun vanished, we would not know for 8 minutes because its last light would still be on its way toward Earth. And if gravity obeys the same speed limit, then the Earth should also continue orbiting the sun for those same 8 minutes before anything changes. Newton's gravity had no way to explain this. In Newton's theory, there is no delay, no signal traveling through space, no mechanism carrying the gravitational influence from one object to another. The pole simply exists instantly everywhere. Even Newton himself was uneasy about this idea. He openly admitted that the notion of objects affecting each other across empty space without any physical connection seemed absurd. But the equations worked so well that scientists accepted the mystery and moved on. Now, Einstein's theory forced physicists to confront it again. If nothing can move faster than light, then Newton's gravity cannot be the final explanation of how the universe works. The theory that had described the motion of planets for more than 2 centuries suddenly looked incomplete, and the tiny anomaly in Mercury's orbit began to look much more important than anyone had realized. Einstein did not begin by trying to fix Mercury's orbit. In fact, the idea that eventually solved the problem came from a much simpler question. A question so simple that almost no one had thought to ask it seriously. Imagine you are inside a sealed box floating in deep space, far away from any stars or planets. There are no windows and no way to see outside. Inside the box, everything is weightless. You float in the air, your shoes float beside you. If you push gently off one wall, you drift slowly across the room until you bump into the other side. There is no up and no down. Now imagine that a powerful rocket engine is suddenly attached to the bottom of the box and it begins accelerating upward. The acceleration is steady, about 9.8 m/s squared. The same acceleration objects experience near the surface of the Earth. Inside the box, something remarkable happens. You feel yourself pushed toward the floor. Your feet press against it. If you drop your shoes, they fall downward. If you toss a ball into the air, it rises slightly and then drops back to the floor. Everything behaves exactly the way it would inside a room on Earth. If you had no window and no way to look outside, you would have no experiment that could tell you whether you were standing on Earth under the influence of gravity or simply inside a rocket accelerating through empty space. To anyone inside the box, the two situations would appear completely identical. This idea struck Einstein with enormous force. He later said it was the happiest thought of his life. If acceleration and gravity are indistinguishable, then perhaps gravity is not a force in the usual sense at all. Perhaps what we call gravity is simply the effect of being in an accelerating frame of reference. Hidden inside this thought experiment is a deeper question that physicists had never really explained. Why do all objects fall at the same rate? Galileo demonstrated this centuries ago. Drop a heavy rock and a light rock from the same height and they hit the ground together. A cannonball and a feather would fall with the same acceleration if there were no air resistance. In Newton's equations, this happens because two different quantities happen to cancel. The gravitational force pulling on an object depends on its mass, but the resistance the object has to being accelerated, its inertia, also depends on its mass. The stronger pull and the greater resistance cancel exactly, so every object accelerates the same way. But these two kinds of mass are conceptually different. One measures how strongly gravity pulls on an object. The other measures how difficult it is to push the object. There is no obvious reason they should be identical, yet experiments have shown they match with extraordinary precision. To Einstein, this was not a coincidence, it was a clue. If gravity and acceleration are fundamentally the same phenomenon, then perhaps gravity is telling us something profound about the geometry of space and time itself. Once Einstein began thinking about gravity in this new way, the consequences quickly became extraordinary. If gravity and acceleration are truly equivalent, then the effects we normally attribute to gravity should appear whenever something is accelerating. And that leads to a remarkable prediction. Imagine again that you are inside the sealed box from the previous thought experiment. The rocket engine is firing, pushing the box upward with constant acceleration. Now suppose a small laser on the left wall sends a beam of light straight across the box toward the right wall from the perspective of someone outside the box floating in space. The light travels in a perfectly straight line. Light always does. But the box itself is accelerating upward while the light is crossing it. By the time the beam reaches the opposite wall, the wall has moved slightly upward. To someone inside the box, the path of the light will not look straight at all. It will appear to curve downward. The beam enters at one height on the left wall and strikes the right wall slightly lower. Now, recall Einstein's key insight. If acceleration and gravity are indistinguishable, then gravity must produce exactly the same effect. That means gravity should bend light. This prediction was shocking because in Newton's theory, gravity acts only on objects with mass. Light has no mass, so Newton's gravity would not affect it at all. A beam of light passing near a massive object should travel in a perfectly straight line. Einstein's theory said the opposite. Light should curve as it passes through a gravitational field. The effect would be extremely small, but it should exist. This idea provided a perfect test. In 1919, the British astronomer Arthur Eddington organized expeditions to observe a total solar eclipse. During an eclipse, the moon blocks the bright disk of the sun, allowing astronomers to see the faint stars located very close to the sun's edge in the sky. If Einstein was correct, the sun's gravity would bend the starlight passing near it, making those stars appear slightly shifted from their normal position. Eddington photographed the stars during the eclipse and compared their positions with photographs taken when the sun was in a different part of the sky. The result matched Einstein's prediction. The light had bent exactly as the new theory said it would. The announcement electrified the scientific world. Newspapers across the globe declared that Newton's theory of gravity had been overthrown. Einstein, who had been an obscure theoretical physicist, suddenly became internationally famous. But the bending of light was only part of the story. The deeper idea behind the prediction was even more radical. Gravity was not acting like a force at all. Instead, it seemed to be changing the very structure of space and time themselves. While the bending of light made dramatic headlines, the most convincing confirmation of Einstein's new theory had actually appeared a few years earlier in a much quieter way. Remember the strange discrepancy in Mercury's orbit? The tiny extra shift of 43 arcseconds per century that Newton's gravity could not explain. For decades, astronomers had searched for a missing planet to account for it, but the planet Vulcan was never found. The real explanation came in 1915 when Einstein completed the final form of his new gravitational theory, what we now call general relativity. One of the first calculations he attempted with the new equations was the motion of Mercury. If his theory was correct, the curvature of space and time around the Sun should slightly alter Mercury's orbit. The planet travels closer to the Sun than any other planet. So, it moves through the most strongly curved region of spacetime in the solar system. When Einstein worked through the mathematics, he discovered something astonishing. The new theory predicted that Mercury's orbit should precess by exactly 43 arcsecuries beyond what Newton's gravity predicts. The unexplained discrepancy that had puzzled astronomers for more than half a century fell directly out of the equations, not approximately exactly. Einstein later wrote that when he saw the result, his heart began to pound. He realized in that moment that he had probably found the correct description of gravity. The reason the new theory solved the problem is deeply connected to its central idea. In Newton's picture, gravity is a force pulling objects toward one another across empty space. In Einstein's picture, there is no pulling force at all. Instead, massive objects change the geometry of the universe itself. Space and time are not a passive stage on which events take place. They are dynamic and flexible. When a massive object like the Sun exists, it alters the geometry of spacetime around it. Objects moving near the Sun simply follow the natural paths determined by that curved geometry. Physicists call those natural paths geodesics. Mercury is not being pulled by a mysterious force. It is simply following the straightest possible path through a region of spacetime that has been curved by the Sun's mass. Because the curvature near the Sun is slightly different from what Newton's theory assumed, Mercury's orbit slowly rotates as it travels around the Sunday. This idea is profoundly different from the traditional picture of gravity. Instead of invisible forces stretching across space, the motion of planets becomes a consequence of geometry. Matter and energy change the shape of spacetime, and the shape of spacetime tells objects how to move. Once you begin thinking about gravity this way, many puzzles that seem mysterious in Newton's theory suddenly start to make sense. To really understand what Einstein's theory is saying, we need to focus on something even more surprising than curved space. The key effect of gravity is actually not the curvature of space, but the curvature of time. Mass changes the rate at which time itself flows. This sounds strange at first, but it is not speculation. It is something that has been measured directly in experiments. Imagine placing two extremely precise clocks in the same room. One clock is placed on the floor and the other is placed on a shelf a few meters higher. According to Einstein's theory, the clock closer to the Earth should tick slightly more slowly than the one farther away. The difference is incredibly small, but it is real. Time runs more slowly in stronger gravitational fields. This prediction was first confirmed in 1959 in an experiment performed by physicists Robert Pound and Glenn Reba at Harvard University. They measured the energy of gamma rays traveling up a tower about 22 meters tall. The photons climbing upward out of Earth's gravitational field lost a tiny amount of energy, which showed that time at the top of the tower was running slightly faster than time at the bottom. Later experiments confirmed the effect with even greater precision. This strange behavior of time is not just a laboratory curiosity. It affects technology that millions of people rely on every day. The satellites used by the Global Positioning System orbit about 20,000 kilometers above the Earth. At that altitude, gravity is weaker than it is on the surface. So the clocks on those satellites tick slightly faster than clocks on the ground. The difference is about 38 micro each day. That may sound insignificant, but if engineers did not correct for this effect, the GPS system would accumulate errors very quickly. Your phone's location would drift by several kilometers every single day. The fact that your navigation works accurately is direct evidence that Einstein's theory is correct. Now, here is the remarkable connection to gravity. Every object in the universe is always moving through spacetime. Even when you are sitting still in a chair, you are moving forward through time. Your watch ticks, your body ages, and the seconds continue to pass. In Einstein's description, the presence of mass changes the flow of time around it. Near the Earth, time flows slightly more slowly than it does farther away. This creates a kind of slope in the fabric of spacetime. When an object is released, it simply follows the natural path through that geometry. That path curves toward the region where time runs more slowly. The result is what we observe as falling. Gravity is not a force pulling objects downward. It is the natural motion of objects moving through a landscape where time flows at different rates in different places. Once you begin thinking about gravity this way, something even more surprising becomes clear. When an object is falling, it is not being forced to move. It is actually moving in the most natural way possible. In Einstein's picture, objects in free fall are not being pulled by anything. They are simply following the straightest possible path through curved spacetime. Physicists call these natural paths geodesics. The idea can be understood with a simple analogy. Imagine two travelers starting at the equator of the Earth and walking straight north without turning left or right. Each person is moving in what feels like a straight line on the surface beneath their feet. Yet, because the Earth is curved, their paths slowly move closer together as they travel north. Eventually, they meet at the North Pole. To someone who does not know the Earth is round, it might look as if some mysterious force pulled the travelers toward each other. But there is no force involved. Both travelers simply walked straight across a curved surface. The geometry of the surface caused their path to converge. Something very similar happens in gravity. Massive objects like the Earth change the geometry of space-time around them. When a ball is released from your hand, it simply follows the straightest path available in that curved geometry. To us, that path looks like a fall toward the ground, but the ball itself is not experiencing a force. If you could ride along with a falling ball, you would feel weightless. This is exactly what astronauts experience in orbit around the Earth. Even though gravity is still acting on them, they feel no weight because they are freely following a natural path through spacetime. This leads to one of the most counterintuitive ideas in modern physics. The person standing on the ground is actually the one experiencing a force. When you stand on the floor, your body is prevented from following its natural path of free fall toward the center of the Earth. The floor pushes upward on your feet. Your bones push upward on your muscles. Your entire body is constantly being forced away from the geodesic path it would otherwise follow. The sensation you interpret as the pull of gravity is really the resistance of the ground pushing against you. In other words, the falling object is the one that is free, while the person standing still is the one being accelerated. Once you see gravity this way, many everyday experiences begin to look different. The feeling of weight is not the presence of gravity, but the interruption of it. The skydiver falling through the air before the parachute opens is actually closer to the natural motion of the universe than the person standing safely on the ground. Free fall is not the absence of gravity, it is gravity itself. When you follow this idea to its extreme limits, the picture of gravity becomes even more astonishing. If mass and energy curve space-time, then extremely massive objects can create regions where that curvature becomes incredibly strong. One of the most dramatic examples is a black hole. A black hole is not simply a heavy object pulling things inward with a stronger force. In Einstein's description, it is a region where spacetime itself is so severely curved that every possible path leads inward. Once something crosses a boundary called the event horizon, there is no path that leads back out, not because a force is pulling objects inward, but because the geometry of spacetime itself has changed. Inside that region, every natural path through spacetime leads toward the center. Even light cannot escape, not because gravity is pulling it back, but because there is simply no outward direction left to follow. Einstein's theory also predicts that spacetime is not rigid. When massive objects move or collide, they create ripples in spacetime that travel outward across the universe. These ripples are known as gravitational waves. For nearly a century, there were only a prediction of the mathematics. Detecting them seemed almost impossible because the distortions they create are incredibly small. Yet, in 2015, the LIGO Observatory finally detected gravitational waves produced by two black holes merging more than 1 billion light-years away. As the waves passed through Earth, they stretched and compressed space itself by a distance smaller than the width of a proton, and the detectors were sensitive enough to measure it. The signal matched Einstein's predictions perfectly. Discoveries like these reveal just how different Einstein's view of gravity is from the one most people learn in school. Gravity is not a mysterious force reaching across space and pulling objects together. Instead, mass and energy reshape the geometry of the universe itself. Space-time curves around massive objects, and everything within that curved geometry simply follows the natural paths available to it. What we experience as the pull of gravity is really the result of objects moving through this curved spacetime. So the next time you drop a cup or watch a stone fall toward the ground, you can picture the event in a completely different way. The cup is not being dragged downward by an invisible force. It is simply moving along the straightest path through a region of spacetime whose geometry has been altered by the mass of the Earth. The universe is not pulling objects together. The universe is curved, and everything inside it is following the paths that curvature allows.